Hey, Physics 30s, it's Mr. Juckley again. This is very exciting. We are on Unit 6, which is our last unit in Physics 30. We're doing our very, very first lesson today. This is nuclear physics, and we're doing nuclear basics today. So we are on lesson 1. If you're not already there, please get your booklet out. And I will also mention that you will need your a little bit of a different data sheet for this. So if I go into my internet here, this is the periodic table that we'll need. Let's see, in Physics 30, we can find this. This is our Google Classroom. If you go to the classwork section and scroll right down to the bottom, here it is in our fundamental skills and data sheet. You click on that data booklet, it will have everything that you need, including this periodic table. That being said, you can use your chemistry periodic table as well. That will work. I typically, through the regular year, encourage students to use the physics one because that's what you get in a diploma, but the chemistry one does work. Okay, so jumping into some nuclear basics, you should know that there are 3 parts of an atom. There are, let me get my felt pen back, electrons buzzing around the outside. There are protons and neutrons within the nucleus. Now we've talked about this in the last unit as a whole and how it relates to EMR. Now we're focusing on just the nucleus, So inside of the nucleus, we've got those protons and neutrons. You know, protons are positive, neutrons are negative. Together, and this is a bit of a new term, together we're going to call them nucleons. So nucleons are protons, neutrons, they are the things that are inside of the nucleus. Cool. We know that the periodic table, this goes back to grade like 8 or something like that, is organized primarily by increasing number of protons. There's a ton of other ways, like the periodic table is so well organized, it's outstanding, but primarily in terms of the number of protons, and we know that the number of protons can be found via the atomic number. So for example, hydrogen has an atomic number of 1, it has 1 proton. Helium has an atomic number of 2. You'll never guess how many protons. 2. Lithium, 3. Beryllium, 4. Boron, 5. Carbon, 6, and so on and so on. I'm not going to go through the whole list, but this is a great way to identify. So if I said, let's pick out something pretty random here, tungsten, and I asked you how many protons tungsten has, well, or sorry, if I asked you to find tungsten, that's what I was going for. You might search back and forth, but if I told you that tungsten has 74 protons, you'd be like, oh yeah, there it is, there's tungsten, it's a W for some reason. Great way to identify things. Okay, so things that we know. Electrons, we know their symbols. Protons, their symbols. Neutrons, just an N for its symbol, so no problem there. Their charge in terms of the elementary charge, an electron is -1. A proton is, that's a P for proton, is +1, and a neutron has no charge. The mass, and this is a new thing that we've got here, this U, this is atomic mass units. Atomic mass units, and 1 atomic mass unit is the mass of 1 proton or 1 neutron. So therefore, proton has 1 AMU. I guess I should abbreviate that before I start saying the abbreviation, atomic mass unit, AMU. A neutron also has a mass of 1, and an electron, for all intents and purposes, has a mass of 0 because they're so flippin' small. So, again, bit of review from Science 10 or whatever. Nuclear notation. So this is where we get into stuff that you may or may not have learned about in Science 10. It's technically not part of the Science 10 curriculum, but I know a lot of teachers go over it very briefly because they know it's going to help you out here. So when I talk about nuclear notation, it's a way to represent different isotopes. We'll talk about isotopes in a split second here, but X is the symbol of the element. Oh yeah, so there's X. So for example, lithium, Li. A is the mass number, which is the total number of nucleons, and Z is my nuclear charge. It's kind of a weird way to put it. Let's think about what kind of things have charge inside of the nucleus. Well, the things that have charge inside the nucleus are the protons, so Z is the nuclear charge, but it's also to the number of protons, and this is in terms of E, or in terms of the elementary charge. Perfect. So let's go back to that lithium. I might have lithium with 7 nucleons in it. So I'd put my mass number of 7 up top. That means a total of 7 protons and 7 neutrons. What's the atomic number of lithium? Well, it's got to be 3, and that's the only way it can be, because if you change that, if you change the atomic number or the number of protons, you totally change what the element is. So this would be my nuclear notation for lithium 7. So 7 being the atomic mass that we see there, right? Or the mass number, the total number of nucleons. Here's a quick question. How many neutrons do I have in lithium 7? Yeah, you got 4 of them, right? So you got 7 nucleons in total, 3 of which are protons. The rest have to be neutrons. Perfect. It's not too bad at all. So maybe put the video on pause and see if you can figure out example number 1. So we're looking at sodium 25, determine nuclear notation, the number of neutrons, protons, and nucleons, the nuclear charge in coulombs. Interesting. Put it on pause, try it out now. Alrighty, so I'm just going to go through an order. The nuclear notation, sodium, I know that is Na. Sodium 25, the 25 tells me my number of nucleons, or my mass number, and that goes up top here. The, let's see, I need the number of protons now, or the nuclear charge. Oh, there's 11 in sodium, so I'm going to put 11 down here. So we've got 25 nucleons. We've got 11 protons, and that means that the rest of those nucleons have to be neutrons. So let's see, I think that would be 14 neutrons. Excellent. Okay, so part 1 and 2, check. The next part is, what is the nuclear charge? So the nuclear charge, we can use this old formula that we made, Q is equal to Ne, except we're not really using the number of electrons in deficit. N is now the number of protons that we have. So it is 11 protons times our elementary charge, which is 1.6 times 10 to the negative 19 coulombs. And you know what I'm going to do? I'm going to even make this so it's both using the formula and using it as a conversion factor. 1.6 times 10 to the negative 19 coulombs for every 1 proton. Protons cancel with protons, and you know what? I have no idea what the answer to this is, so I better get out a calculator. 11 times 1.6 times 10, there it is, negative 19. So that's going to be 1.76 times 10 to the negative 18 coulombs. Cool, we even have the nuclear charge. Fantastic. Alrighty. So I've mentioned this before, isotopes. Elements of the same type need to have the same number of protons. So for example, hydrogen, no matter what, has 1 proton. Helium, no matter what, has 2 protons. If you were to add an extra proton into hydrogen, it wouldn't be hydrogen anymore. It would all of a sudden be helium, right? So you have to have every single hydrogen atom, no matter what, has 1 proton, and that's it. Every single helium has 2 protons, and that's it for protons. You can't go down, you can't go up, or else it's not helium anymore. But what you can do is you can change the number of neutrons. So you can have different numbers of neutrons, and therefore different masses. So as an example, we've got hydrogen 1, hydrogen 2, and hydrogen 3. The thing that's missing with this is our atomic number. It should go there. And same with helium. There are 2 common isotopes of helium, so helium 3 and helium 4. Cool, all right. So change the number of neutrons, change the mass. That being said, all isotopes have the exact same chemical properties. Their physical properties are a little bit different, but their chemical properties are exactly the same. So for example, all 3 of these hydrogens, whether it's hydrogen 1, hydrogen 2, or hydrogen 3, well, they all make water, right? Water might be a little lighter, a little heavier. They all make water, though. Okay, so let's think about this nucleus a little bit more. What's inside of the nucleus? A whole bunch of protons, which are a whole bunch of positive charges, and a whole bunch of neutrons, which have no charge. A whole bunch of positives right next to a whole bunch of positives. Is that a happy place for those protons? positives next to positives. Not really, right? Because there's an electric force that's trying to repel protons from protons. So what holds the nucleus together, I guess, is the question then. Well, it's our nuclear strong force. And there are actually four fundamental forces that we've mentioned before. There's the nuclear strong force, there's the electromagnetic, there's the nuclear weak force, and then there is the force of gravity. The nuclear strong force that we're focusing on right now is clearly the strongest of the forces. Things to note about this. Of all our four fundamental forces, this is the strongest. Things to note about this. It is always an attractive force. No matter what, it is an attractive force. Other things to note, it acts between any pair of nucleons. So between a neutron-neutron, neutron-proton, or a proton-proton, it acts between them all. Awesome. So that's actually pretty handy, especially the proton-protons, because we want to stick them together. Something to note, it is a short force in quotation marks, which means it works only over very, 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 very extremely small radii or distances. So this is 10 to the negative 15 meters. If I'm at 1 times 10 to the negative 15 meters, I got a decent strong force. If I'm at 4 times 10 to the negative 15 meters, I have pretty much no strong force. Right? It decreases so quickly with distance. It only really works on these nucleons that are just so close together. Just so close together. Okay. Next thing that we want to talk about is, so we know what's inside of the nucleus. To start anyways, we'll learn some pretty crazy stuff as we go through. We know what holds the nucleus together. It's the nuclear strong force. The next thing is, something funky goes on when that strong force is actually happening, when we're actually holding a nucleus together. So scientists have discovered that the actual mass of the nucleus is actually less in every case than the total mass of the individual nucleon. So let's think about that for a quick second here. If I had something with, say, 4 nucleons, I don't even care what they are, and they're totally separate, when they come together and they make a nucleus, and those 4 nucleons are together, this has less mass than the individuals, which is pretty weird, right? Pretty weird. This is called the nuclear mass defect. And if I ever wanted to figure out my nuclear mass defect, all I need to do is take the difference between my total and my actual. Now, I know that delta typically means change in, and it's final minus initial, which would make this backwards and would make it a negative number. Honestly, it doesn't really matter. You can take the absolute value. So I'll just show you that really quick. Delta M is equal to mass final minus mass initial, if we're going with classic delta, right? And we might say that these things are coming together like I've drawn up here. So this would be mass final, and this would be mass initial. So if mass final is less than mass initial, we might get a negative number. That negative number just represents the mass decreasing, right? Which makes sense. So just take the absolute value. All I'm trying to say with this, it doesn't matter which one you subtract from the other, just take the absolute value if you end up with a negative number. Cool. Oh, I went way too far forward. Okay, so the nuclear mass defect. So where does that mass go? Well, it's Einstein, and this is where we're getting in Einstein's most famous equation of all, E is equal to mc squared. Einstein proposed that that mass was actually just another form of energy. And the formula that explains that is the energy from the mass defect is equal to delta mc squared. Delta mc squared, where delta m is the mass defect, has to be in kilograms, c is the speed of light, and E is the energy, and has to be in joules. Has to be in joules if we're using this formula. Cool. So what he proposed was, it is the energy released as that nucleus comes together. So the mass defect actually is the energy released as it comes together. It's our nuclear binding energy. It's kind of like the energy that holds that nucleus together, right? So it's the energy that holds the nucleus together. We could look at it another way. We'd have to add that much energy in order to bust that nucleus apart. Cool. One big thing to know with this is, well, before today, in our high school careers, we've had the conservation of energy. And separately, we've had the conservation of mass, but now we're saying mass and energy really aren't that different, so we need a conservation of mass energy. Conservation of mass energy. And here's a really quick question for you. What physics principle are we talking about? It's physics principle 6. And if we wanted to write this out in terms of kind of a formula, I'd say my mass energy before is going to be equal to my total mass energy after. So very similar to our conservation of energy, but we have to include that mass energy. Cool. So a quick question right off the bat with this. We want to determine the nuclear binding energy of copper 65. Okay, so let's think about this for a second. Copper 65. What does that 65 tell us? That's the number of nucleons. The total number of nucleons that are in that. Awesome. And then it tells us there's 64.928 U. Do you remember what U is? U is our atomic mass units. So this is our actual mass is what we're talking about here in terms of atomic mass units. Awesome. Okay, so we've got that. Now I want you to get out your data sheet and I want you to look at something for me. So what is an atomic mass unit? And this is on the back of the data sheet, or what I like to call the back of the data sheet. What is an atomic mass unit in kilograms? See if you can find that on the back of your data sheet. Go for it right now. Put it on pause if you have to. Cool, so I'm looking under the constants. I'm looking at the middle left-hand side. It says 1 atomic mass unit is equal to 1.66 times 10 to the negative 27 kilograms. So 1 atomic mass unit, so that is a mass unit of something inside of a nucleus. But what's the mass of an individual nucleon? So this is inside nucleus. So an individual nucleon, the mass of a proton or a neutron, what do we know that as? So now I'm looking at the right-hand side of our data sheet. It's 1.67 times 10 to the negative 27 kilograms. So this is all by themselves, or before they're in a nucleus, by self. So an individual proton or neutron has a mass of 1.67 times 10 to the negative 27 kilograms when it's all by itself. When it's locked inside of a nucleus, we start to look at that atomic mass unit and we say, oh, well, now it's 1.66 times 10 to the negative 27, right? So individual protons, neutrons, 1.67, atomic mass units, 1.66. Okay, now that we have that, we can go through and we can actually try and solve for this. So we know that we're using, E is equal to delta mc squared. It's supposed to be an E. It's equal to delta mc squared. So I probably need to figure out delta m first. So let's go ahead and figure out delta m. Delta m is going to be equal to my mass of the individuals, so my total mass of all the individual nucleons, minus my actual mass of the nucleus itself. Okay, but can I just do 65 minus, what was it, 64.927? No, right? Because the 64.927 is based on 1.66. The 65 is based on 1.67. So what I need to do is I need to use my total mass, so that is 65 individual protons and neutrons, each with a mass of 1.67 times 10 to the negative 27 kilograms. I need to use that in kilograms, and I need to subtract that, or sorry, subtract from that, if I could speak correctly here, 64.928 atomic mass units times 1.66 times 10 to the negative 27 kilograms. And I'm even going to turn this into a conversion factor, kilograms per atomic mass unit. So I've got kilograms minus kilograms. All right, so take a moment, plug that into your calculators. Remember, you don't want to round this till the very, very end. What we should end up with is 7.6952 times 10 to the power of negative 28 kilograms. Awesome. So I got my mass defect. Or we've got our mass defect. If we wanted to figure out the binding energy, well, that's easy, because now we can just go through and say, oh, thank you, Einstein. E is equal to delta mc squared. E is equal to, okay, well, delta, and we just figured that out, 7.6952 times 10 to the negative 27 kilograms times the speed of light squared, so that's 3 times 10 to the power of 8 meters per second squared. And let's see, plug this in. I get 6.93 times 10 to the power of negative 11 joules. All right, so we got our nuclear binding energy, 6.93 times 10 to the negative 11 joules. One thing I want you to think about with this is, you look at this 10 to the negative 11 joules, is that a lot of energy? Not really, right? But we're talking about one nuclei, or one nucleus for copper. When you hold a thing in your hand, like 63 grams roughly of copper in your hand, you're dealing with a mole of those individual nuclei. So when you put this in the scale of like stuff that we can actually touch, this is actually a very large amount of energy. And we'll look at that as we go through the course. There's a ton of energy stored within the nucleus of atoms. It's actually pretty crazy how much energy is actually there. So anyways, we've got this idea here. We can figure out our nuclear binding energy. So that's how much energy it takes to hold that nucleus together. It's also how much energy it's going to take to bust it apart. Oh, there's some space for me to work. Last thing that we want to talk about is just kind of a funky little unit for mass and mass energy. So, whereas before we've always used kilograms for energy, and in a lot of places we still need to use kilograms for energy, but physicists, especially nuclear physicists, are more interested in the energy side of things than the mass side of things. So they developed a new unit for mass that essentially talks about it in terms of its equivalent energy. So mass, where did it go there? Mass in terms of equivalent energy, and the unit is electron volts per speed of light squared, or EV per c squared. It's kind of a weird one. Definitely kind of a weird one. Let's have a look at how it works here. So we want to, I think this is the wrong question there, yeah. Okay, this is what we want to look at here. Determine the mass energy of a proton in mega electron volts per speed of light squared. Just writing down a note on the sideboard there for you for after. Okay, so things that I'm looking for. First thing that I'm going to do, if I'm thinking about the mass energy, so I'm thinking about the mass, but in terms of energy, we're going to use Einstein's equation, E is equal to delta mc squared, to figure out the actual energy. So in this case, we're using a single individual proton, so that's 1.67 times 10 to the negative 27, 7 kilograms. And we're going to say how much energy would that entire proton be, or that entire mass be? So we're going to multiply it by 3 times 10 to the power of 8 meters per second. And of course, we're just going to square that. E is equal to mc squared. So when I go through and when I plug this in, we end up with 1.503 times 10 to the power of negative, where'd that go there? Negative 10 joules. Okay, cool. Now you probably already guessed with the question, we don't really want joules, we want electron volts, in particular mega electron volts. So I'm going to take this energy, so 1.503 times 10 to the negative 10 joules, and I want to convert it into electron volts. So electron volts has to go on the top, joules has to go on the bottom. I know that for every 1 electron volt, it is 1.6 times 10 to the negative 19 joules, so joules cancels, and we end up with 9.39 times 10 to the power of 8 electron volts, which we could go ahead and say is 939 mega electron volts, just because our question is asking about mega electron volts. Cool. So 939 mega electron volts. That's how much energy the mass for one single proton would be. Cool, okay. Now if I want to talk about in terms of mass, well, this is where it gets a little bit funky. E is equal to delta mc squared. Delta m is equal to E over c squared. So this is 939 mega electron volts by speed of light squared. And that's it. You leave it. You don't actually divide by speed of light squared, because then it wouldn't really be in terms of energy anymore. You'd be getting, well, nothing realistically, because mega electron volts and speed and meters per second will go too well together. So we just leave it in terms of mega electron volts. It's the energy, but kind of more talking about the mass. Cool. So that is our first lesson, folks. One thing that you should be able to do actually, and think about this one for a second, is could you go from 939 mega electron volts per speed of light squared? Could you work backwards and figure out how many kilograms that is? I'll leave that to you though. Anyways, I'll stop chatting now. It's good working with you, Physics 30s. I really enjoy chatting things with you. Can't wait to see you again. Yeah, I'll leave it there. Bye for now, everybody.